So sorry for the disturbance. I think that my mic was not open. So here, so today we are going to learn about the capacitor in the revision series. This is a continuation of revision series of conductor. So today that we are going to cover the electrostatics of conductor, dielectric, what is dielectric, capacitance and parallel plate capacitor, obviously, and the capacitor with dielectric. So these are all the concept of related to capacitor that we are going to discuss today. Okay. Now, the very first is the introduction to capacitor is the electrostatic of conductor. Now, we know that a conductor is nothing but which can allows the of electricity through it. Okay, so that is defined as the conductor which can conduct electricity through it. So that property of any material makes it a conductor. Okay. So generally metals are the example for conductor. Okay, although there are other materials also that behaves as a conductor and allows the current through it, but metals are the most general and most specific examples that we have. So what we have did, we have placed a piece of conductor in an external electric field, let's say E vector, and we will see then what will happen to that conductor. Now, the very first thing that can happen to this conductor is, the very first statement is electric field inside the conductor is zero after steady state is achieved. Now, what is this steady state? So look that there we have a conductor, let's say, and we have there is no external field applied to it right now. So the free electron inside the conductor will move randomly and they cancel out the effect of current inside the conductor, and the current inside the conductor or the electric field developed inside the conductor is zero. Okay, because the motion of that electric field, that free electrons are so random that they cancel out the electric field developed by each other, and the net electric field, if you talk about in a, is equals to zero. Now, when we place this conductor in an external electric field, which is E vector, let's say, so what will happen then? What will happen? These electrons will move towards the opposite direction to the applied electric field. Let's say this is the direction of electric field. So these electron will move is at this side opposite to the field, and the positive charge will move to the in the direction of electric field. So finally, what do we have? We have a surfaces like this. Okay. Now, if you talk about the inside point, these are the surfaces. So these charge align themselves to the surface of the conductor. So there is no charge inside the surface, inside the conductor, which results in no electric field inside the conductor. So this is the first statement that we have. Now, potential inside the conductor and on the surface is the same. Now we know that potential is nothing but the work done to bring the charge particle from infinity to a particular point. Now, if you bring that charge particle from outside, you will face these charges as the resistance. Okay, you will have to work in the field of these charges. But if you place that on surface, and we will also see in the previous lecture, we have also seen that for a spherical charge conductor, the potential inside is equals to the potential at surface. Okay, and also from the relation between electric field and potential difference, we can say that delta V is equals to minus E into delta R, E dot delta R. So if inside the electric field is zero, which means the change in potential is also equals to zero, which means inside any point of the conductor, the potential will not change. It has a constant value, same as the surface. Now, the next point that we have is electric field on the surface is normal to the surface. Why? Let's say this is the positive charge and we will assume that any random direction of electric field, that this is the electric field developed by this charge. So this is has a component in the direction of surface. This is the E parallel to the surface. So it means that charge will also move toward this. And moving this charge, we need to done some work. But we know that for because the charges and the electric field, because the charges are distributed in such a way that the potential difference on the surface will be zero, which means we do not have to done any kind of work. And from this definition, we have to do some work, which means that this is not correct because charge will also move parallel to the surface. Okay. So in this case, there is another work. So this is not happen. So that is why only perpendicular component, or we will say that electric field is always normal to the surface of conductor. Okay. Now, based on that, we have a PYQ. Statement 1 said that electric potential is constant within and at the surface of each conductor. Statement 2 that electric field just outside a charged conductor is perpendicular to the surface of the conductor at every point. Now, statement first says that the electric potential is constant within and at the surface of each conductor. Yeah, obviously, correct. We have seen it. Now, electric field just outside a charged conductor is perpendicular to the surface of the conductor at every point. Yeah, obviously. Because if there is a surface component of electric field, the charge will also move on the surface and there is a development of current. So this is not happening. This is not happened. That is why we are making this conclusion. Okay. So we can say that both statement 1 and 2 are correct. Now, in a metallic conductor, under the effect of applied electric field, the free electrons of the conductor now move in the straight line path in the same direction, movement with the uniform velocity throughout from lower potential to higher potential, or drift from higher potential to lower potential. And another is move in the curved path from lower potential to higher potential. Now, if this is the conductor, initially there is no electric field is applied, so this is the free electron we have. So they have a random motion in every direction. So we can say that they can nullify the total effect of the current, or total electric field. So E is 0 in this case. Now, if we applied the electric field, the electron will move in opposite direction to the electric field. So this charge will, this side will be negatively charged and this side automatically will be positive charge. Okay. Now, the electron inside the conductor, there are heavy immobile charge ions. Okay. Because of that, this electron will collide with these. Okay. And that is why, because there is a random motion of electron also. So it is same as if there is a river. Okay. And river is still, and you throw some let's say throw your shoes on that, and they will be at still, at the water is still. But if you take a boat and river is let's say downstreaming from the river velocity is this is the velocity of river, and this is the velocity of your boat. So what will happen to you? Because of this river current, you will also drift in that way. So because of reaching this point, instead of reaching this point, you will reach at this point. So this is called the drift, which means you have your own velocities, but due to the some external effect, you drift yourself from to the actual point. So that is why we can say that electron, which also has their random motion, but because the externally applied field, they drift in the direction of electric field. Okay, obviously from higher potential to lower potential. So because higher potential we assume the positive one, and lower potential we assume the negative one. Okay, so option C is the correct option. Now, a point charge 2 into 10 raised to the power minus 2 is moved from P to S in a uniform electric field 30 Newton per coulomb. Okay, directed along the positive x-axis. If coordinate of P and S are 1, 2, 0 and 0, 0, 0 respectively meter, the work done by electric field will be. Now, we can say that if this is the coordinate system, the coordinate of P is 1 into 2. Let's say this is 1, 2, 3 in the x-axis. And this is 1, 2, 3 in the y-axis. So coordinate 1 to 0 means coordinate of point 2 will be this 1 to 1 comma 2 comma 0. This is the coordinate of P, and 0 comma 0 comma 0 is the coordinate of origin. So we have moved from P to S. So this is our displacement vector. Okay. Now there is an electric field which is directed in the direction of positive x-axis. So if I want to write this electric field in the vector form, we can write the magnitude into directional vector. Now to find the work done, what is the formula for work done? Work done is Q into delta V. Okay, we can say that. And also delta V, how do we find delta V? So we know that delta V is nothing but minus of E vector dot delta R vector. Now our job is to find delta R vector, then find delta V, and then find. Now how to find delta R vector? So delta R vector is nothing but R final minus R initial. Now R final vector is this, sorry, final vector is 0 I cap plus 0 j cap plus 0 k cap. 0 I cap plus 0 j cap plus 0 k cap. Minus initial vector is 1 I cap, means I cap plus 2 j cap plus 0 k cap. So we can say that it is minus I cap minus 2j cap. This is the displacement vector in meter. So we can find out the potential difference delta V. It is equals to minus E vector dot R vector minus E vector dot delta R vector. E vector we know it is 30 I cap minus delta R multiply with dot product with delta R vector, which is minus I cap minus 2j cap. This should be resultant in minus into minus, because this will become minus 30 I cap. Minus 30 I cap will dot product with I cap. So it will become plus 30 into 1. And 30 I cap dot product with 2 j cap. So I cap dot j cap will become 0. So rest of the thing will be 0 here. So we have 30 volt potential difference. Now work done will be Q, that is charge, multiply by the potential difference. So charge is given you as 2 into 10 raised to the power minus 2 coulomb, and it is 30. So it will become 6 into 10 raised to the power minus 3 joule. Now you can say it that It is given in the question that these things are in millijoule. So we can convert it into millijoule. So 1 joule has 10 raised to the power 3 millijoule, and it will become 2 into 30 will be 60. Okay. So I can say it, and this is 10 raised to the power minus 2. So I can write it as 600 into 10 raised to the power minus 3 joule. So this will become 600 millijoule, because in 1 millijoule we have 10 raised to the power minus 3 joules. Okay. Now, hi Roshni Kharadi, hi Mahisagar, how are you? Good evening. Very good. So we are discussing some question here. Now, the next topic that we are going to discuss is dielectric. Okay. Now, in dielectric, what is a dielectric? In capacitor, we will learn about it. So dielectric is nothing but it is an insulator or non-conducting material. Okay. So each and every insulator or non-conducting material, we can say that this is a dielectric material. Okay. These are of two types: polar dielectric and non-polar dielectric. Hi Dhruvi, good evening. Why have you guys joined late? Don't you know about the timings of classes? So polar dielectric and non-polar dielectric. Polar dielectric is made of polar molecules, and non-polar dielectric made of non-polar molecules. Okay. So we know that the polar molecules and non-polar molecules. So non-polar molecules are in such a way that their centers are coincide with each other, but the polar molecule have a permanent dipole moment. Okay, so these are the properties of it. Dipolar molecule have permanent dipole moment, and they are also, but they do not have any no permanent dipole moment. Okay. Now, if we put the dielectric in an external electric field, then what will happen to it? We are going to discuss how it behaves in an external electric field. So let's say this is the dielectric we have, and we will generally talk about the non-polar, sorry, for polar. So what is happen that if you place, if there is no external electric field initially, there is no external electric field, so polar molecules are arranged in a random manner, plus minus, plus minus, or I will denote them by these. These are the dipole moment vector. So these are randomly distributed when there is no electric field. Okay, but in a case of absence of electric field. Now, if I apply an external electric field to this point, to the dielectric, so this is the case. When electric field is applied to that, these dipole will align themselves in the direction of electric field. We know this from the definition of electric field dipole in an external electric field. Okay, so we know that the dipole will align themselves in the direction of applied electric field. Okay, got it? So because of that, they will have a induced electric field inside them. We know that if the dipole moment in axial direction, so the electric field will be in opposite direction to that. Okay, so they will develop, or also you know that dipole moment, that is p vector and e vector, are opposite in nature, because e vector we know that it is from negative to positive, and dipole moment we measure from positive to negative. Okay, so here we can say that inside, because they are in this direction, so electric field develop will be in opposite direction, this. And let's say this field is ep. Okay, and externally applied field is e naught. So what will this ep do? This ep inside of the material, this ep will reduce this electric field. Okay, got it? Now e net, if you talk about what is e net, e net will be e vector minus ep vector. Got it? So we know that finally, because this is subtracting something from it, from the external electric field we are subtracting something, so it will be definitely lesser than the original value. So we know, we assume that the e net is nothing but e original divided by k times, where k is the dielectric constant. Dielectric constant. Okay, now if I put this electric field in this direction, E net would be E by K is equals to E minus EP. EP is the induced electric field inside the dielectric. So it will be EP is equals to E by K minus E. So we can say that, sorry, it is E minus E by K. E minus E by K. So electric field induced will be E into 1 minus 1 upon K. Okay. So that much amount of the electric field is developed inside the dielectric when it is placed in an external electric field. Now, capacitance. Now, what is a capacitance? Before capacitance, you should know about the capacitor. Now, what is a capacitor? So, capacitor, just a second. Capacitor is a group of conductors और ग्रुप की जगह we will write is a system of conductor. Conductor, conductor may be charged conductor, which stores the electrical energy in it. Electrical energy in the form of electric charge. So capacitor is nothing but which can store the electrical energy in the form of electric charge, and it is a system of conductor that has been placed at some distance, so that they can store some kind of electrical energy in the form of electric charge. That system is termed as the capacitor. Okay. So let's say there are two conductor. This is of plus q charge, this is of minus q, and they are separated by a distance d. So this arrangement is termed as a capacitor. This is a capacitor. Now, we know that these charges, if the potential charge is plus q, so plus potential, it will have higher potential, and for minus q, it has a minus v, which is the lower potential given to this surface. Now we know that if we increase the charge, the electric field in between will also increase, because electric field is nothing but kq upon r square. So it will directly depend on the charge. If you double the charge, the electric field will be double. If you half the charge, the electric field will be half. So E here is directly proportional to Q. Now, we also know that this electric field is equals to, we know that dV is equals to minus E vector dot dr. We can say that the potential is directly proportional to electric field, and electric field is directly proportional to charge, which means if I increase the charge, the potential will increase, and hence the electric field. So I can say that the ratio of q upon v, charge upon potential, is the constant, because they are increasing in the same manner. Okay, initially if the charge is q, this is v. If I double the charge, the potential will be double, because it is directly proportional to e, and e is directly proportional to q. So 2q by 2v will cancel out. So this ratio is always remain as a constant. And what is this constant? This constant is called the capacitance, is denoted by c. So this is termed as the capacitance. Now, from this information, you cannot say that C depends on Q or C depends on potential. No, C will not depend on the potential and the charge. Okay, none of them. C will depend, the capacitance will depend on the size of conductor. Okay, size of conductor, shape of conductor, and separation between the conductor. Separation between the conductor. So always remember that the capacitance, by the formula you can see that V is equals to Q is equals to CV. So C will depends on voltage and charge. No, C will also only depends on the size of conductor, shape of conductor, and the separation between the conductors that we have put. Okay, I hope you are clear with this. If you have any kind of doubt, you can ask anytime. Now, this is for your homework, that to find the capacitance for spherical and cylindrical capacitor. It is just for your knowledge. Okay, there are very less chances that question can be asked from these topics. So please derive it from the for the better understanding that how the capacitor to be find. Okay, and if there should be a if there is a chance to be asked the question, that would be nullify for your side. Okay. Now, for parallel plate capacitor, how do we find the capacitance? Now, let's say these are the positive charge plate. So in respect to that, this plate will be negatively charged. We know that from each plate, the charge will be the electric field of this plate, let's say E1, and the electric field of this plate is the E2. Okay. So E1 here is nothing but we can say sigma upon 2 epsilon naught. We have seen this expression in the Gauss law. Okay. When we find the electric field for the infinitely charged plane, uh, infinitely charged long sheet, we have find out. And E2 is also, we are only interested in the magnitude. So it is also sigma upon 2 epsilon naught. The same charge we have given to it. Inside, if you will see at this point, the electric field, this positive charge will be away from the positive charge. And this from this negative charge, it is towards the negative charge. So the resultant field is also in the same direction. So we can say that E net here is sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught, which is sigma upon epsilon naught. Now sigma is nothing but, I am replacing this E net with E. Sigma is nothing but Q upon E into epsilon naught. So this is the electric field. Now we know that electric field, there is another formula. The change in potential is equals to minus of electric field dot delta R vector. Now suppose the separation between them is delta D, sorry, is D, and we have moved from this point to this point with a displacement of delta R. Now we have moved in the direction of electric field, so potential will be decreased. So that is why it is written here. So delta V is written as V plus V final minus V initial is equals to minus of E, which is Q upon A epsilon naught into delta R vector. So delta R vector is this. Delta R is nothing but, if I move from positive plate to negative plate, this delta R is nothing, is D. Okay. So it will be D. Now, for this purpose, we can say that this delta V or V plus minus V minus is equals to minus QD upon A epsilon naught. Why is this minus? Because we know that if we move in the direction of electric field, the potential will be decreased. So this is the potential. Now, for the solving purpose, we will take it positive because we know the reason that why this minus has been come. So we will say that V is equals to QD over A epsilon naught. Now we know from the definition of capacitance that Q is equals to C times V. So if we put the value of C in terms of, if we put the value of V in terms of Q and C, it will be Q by C is equals to QD upon A epsilon naught. Now Q and Q will cancel out. So C you will have as A epsilon naught by D. So from here you will say that it will depends on the area and depends on the separation. And area will depends on the size and shape of any conductor of any particular material. So this is the capacitance that we have. A epsilon naught by D. Now, electric field in between. In between electric field, I have already discussed it with you, that in between, if this is the positive plate, so same opposite charge will be here due to polarization effect. So electric field will be, net electric field will be in this direction. So I can say that electric field inside is sigma upon epsilon naught. And sigma you will also write E is equals to sigma upon epsilon naught. Sigma is nothing but total charge upon area. So Q upon A into epsilon naught. Okay. This is the electric field in between. Okay. Now, potential difference between plate. Simple. Potential difference between plate. We know that Q is equals to CV. V is equals to Q upon C. C have already calculated A epsilon naught by D. This D will go up. So V here is QD divided by A epsilon naught. This is the potential difference between these plates. Okay. Now, force between the plates. Very simple. So let's say this is the positive plate and we want to know the force, and this is negative plate. We want to know the force between plate, like this, force applied by this plate is same as the force applied by this plate because of the Newton's third law. Okay, so we will assume that this positive plate has an electric field away from it, and this electric field is applied on this negative charge. So negative charge will feel a attraction force. F will be in opposite direction to the electric field. So we can say that F is equals to Q, which is the charge on the plate, into electric field on the another plate. So electric field we have taken for this, and charge we have taken for this. So F here is equals to charge, let's say Q, which is given to this plate, and electric field of this plate, only this plate we are interested. So it will be not net field. So it is sigma upon 2 epsilon naught. Now F is equals to Q into sigma. Sigma is also Q upon A. So it is Q upon 2A epsilon naught. Then force will become 2 square upon 2A epsilon naught. So this is the force experienced by each of the plate. Okay, because if this plate, let's say plate number 1, will apply the force, attractive force on this plate, so this plate will also apply the same force in the opposite direction because of the Newton's third law. For every reaction there is an equal and opposite reaction. So this force will be for both the plate. Okay. Now, energy stored in capacitor. Let's say this capacitor is positively charged. This capacitor is negatively charged. So energy store we will give by, we know that energy is equals to what? Or the most general formula, that potential is nothing but potential energy per unit charge. So potential energy is equals to Q upon potential energy equals to Q into V. Okay. Now V is the potential difference, but we cannot apply the same for here, because here if you will see, this charge that is acquired by this capacitor is not instantly acquired. It is acquired for a time period, because the capacitor will not instantly charge. Okay, that is why it is a passive device. So we will take this as dq here. Now U is equals to V into dq. If you integrate it, so this energy will also be du. If you integrate it, the V is constant because the potential difference that we have applied is constant. Okay, we are supplying the power through a battery which has a constant potential. So dq is equals to integration 0 to so if we put the value of v here, v will be, from the definition of this, v is qd upon a epsilon naught, or simply it is q by c. We can say that it is q by c if we are talking in terms of q. So it is q by c into dq. Now integration of q dq will become q square by 2. So potential energy you will have as q square by 2c. Okay. And if charge is from 0 to capital Q, because we are dealing in terms of capital Q, so potential energy will be capital Q square upon 2c. If you put the value of, this is formula number 1. If we put the value of Q as CV, so it will become C square V square divided by 2C. C and C will cancel out. So you will become 1 by 2 times CV square. This is formula number 2. And if you put the value of C in terms of V, then you have a relation between Q and V. Okay. Now, this is the last case that we are going to discuss. Now, what happens when a dielectric is inserted in between the plates of the capacitor? The case number 1 is when isolated capacitor is there, which means it is not connected to any battery. There are terminals, but they are not connected to the battery. So what will happen if you put the dielectric inside that? It will not get any kind of effect. Okay, but if you connect it with the battery, now there is an electric field developed in the direction of the potential, applied potential. So this is the electric field, and if you place the dielectric inside it, it will reduce, because there is an induced electric field in opposite direction in the dielectric, let's say ED. This ED will reduce the net value of this E between the plates. Got it? So electric field will be decreased when when a dielectric is placed inside the plate of parallel plate capacitor. Okay, so it will get reduced. Now the time is up. So we have covered the most of the topics of this capacitor series. Now from the next day we will discuss about the current electricity, and rest of the topic that you will assume that some of the topic has left of this capacitor. We will discuss them when we get the chance. Okay, and but from the next class we are discussing about the current electricity. Okay, and with the along with PYQs. Okay, so thank you so much for being attentive, and please be join on the time. Yeah, the timing of the class is 3 p.m. 3 p.m. to 4 p.m. Okay, so try to join by 3 5 or 3 7 3 3. Okay, so please be on time. Okay, thank you so much. Thank you so much for being attentive. Take care of yourself, study, keep study, do the hard work to achieve your aim. Okay, thank you so much.